Let's talk about various sums and products when using either irrational or rational numbers, or possibly both. First, we're going to prove that the sum and the product of two rational numbers are both rational. So let x be equal to a over b, and let y be equal to c over d, where a, b, c, and d are all integers. So we've written out two rational numbers explicitly using the integers. Okay. Then x plus y is equal to a over b plus c over d. And then if I write this as with a common denominator, it's a times d plus b over c over b times d. And we observe that the numerator and the denominator are both integers. A and d are integers, so the product is an integer. B and c are integers, so the product is an integer. This product is an integer, this product is an integer, so the sum is an integer. Likewise, b times d is another product of integers, and so that product is an integer. And so therefore, x plus y is rational. And we have that the product, x times y, is equal to a times b, a over b times c over d, which is equal to a times c over b times d. And once again, that is also one integer divided by another integer, because the numerator, the product of two integers, and the denominator, the product of two integers, are also both integers. So the sum, x plus y, and the product, x times y, are both rational numbers. And so that's the end of the proof for the first part. The second part asks us to prove that the sum and product of a non-zero rational number and an irrational number are both irrational. Okay, so let x be equal to a over b, or let x be, say it another way, let x be rational, but not equal to 0, and let y be irrational, so it is a real number, but not rational. Okay, we're going to prove this by contradiction. So suppose that x plus y was rational. Suppose x plus y is rational. Then, if x plus y is rational, then by the thing that we just proved, then x plus y minus x would also be rational. Or that y is rational. But that can't be because y is not a member of the rationals, so that can't happen. For the second part, let me do this in a different color. Suppose that x times y is rational. Then if I divide, because q is a field, and I'm dividing by something other than 0, then the quotient must also be rational. And again, that is a contradiction. So our conclusion is that both x plus y and x times y must be irrational numbers. And that's the end of the proof. For the other questions basically illustrate that if you have two irrational numbers, you never know what you're going to get. So exhibit two irrational numbers whose sum is irrational. Well, if I take the square root of 2 plus the square root of 2, so there's two irrational numbers. If I add them up, I get a second irrational number, 2 times the square root of 2. 2 is rational, square root of 2 is irrational, so the product 2 times the square root of 2 must be irrational by the thing that we just proved. Exhibit two irrational numbers whose sum is rational. Well, we can do this, square root of 2 plus negative square root of 2. Negative square root of 2 is negative 1 times square root of 2. Negative 1 is rational, square root of 2 is irrational, so negative square root of 2 must be irrational. So I have two irrational numbers. Add them up, I get 0, which is a rational number. Exhibit two irrational numbers whose product is irrational. So if I take the square root of 2 times the square root of 3, then that would be the square root of 6. And so irrational times irrational could be irrational. But I could take two irrational numbers, like the square root of 2 times the square root of 2, and the product could be a rational number. So if I take two rational numbers and add and multiply, I get something that's rational. If I take a rational, non-zero, and an irrational, and either add or multiply, I get something that is irrational. But if I have two irrational numbers and add and subtract, then I really don't know what I'm going to get. So I have all these possibilities here.